Good afternoon. Welcome to Goddard Space Flight Center and today's Space Astronomy Update, where we will have today some of the most dramatic pictures yet from the Hubble Space Telescope. And here to tell us about it and the findings is our distinguished panel and our host, Steve Marin, an astronomer from Goddard Space Flight Center. Steve?
Thanks, Don, and welcome to Space Astronomy Update, everybody originating today from Goddard Space Flight Center in Greenbelt, Maryland. And with us today to discuss the birth pangs of stars like the Sun and its solar system are three experts who've been investigating these objects with the Hubble Space Telescope. Professor Jeff Hester from the Arizona State University in Tempe, an investigator of nebulae of some distinction, and a member of the original Wide Field and Planetary Camera team for the Hubble Space Telescope. And also we're glad to have a young postdoctoral researcher, Dr. John Morse of the Space Telescope Science Institute in Baltimore, did his PhD on these objects at University of North Carolina, a Harvard graduate. And welcome back to Space Astronomy Update, one of the optics experts of the Hubble Space Telescope, a member of the Wide Field and Planetary Camera 2 team from the European Space Agency and Space Telescope Science Institute, Chris Burrows, Dr. Chris Burrows. And our independent panelist, Chairman of the Department of Astronomy at the University of Washington in Seattle, Dr. Bruce Margon, who is the Chairman of the Board of the Astrophysical Research Consortium and just appointed as the next Chairman of the Board of the Association of Universities for Research in Astronomy. Head of two boards, but he won't leave any one board because he's one of the brilliant communicators of astronomical research. Now, we're talking about Herbig-Haro objects, and Jeff Hester, what are they and what have you seen with the Hubble telescope?
Well, I'll back up a little bit and first start talking about why it is that star formation is such a fascinating question. When we look at stars forming, astronomers never get a chance to actually see stars forming. But what we can do instead is look out at different objects and catch them at different stages in the formation process, and then use what we know of physics and of our local environment to put those together into a story, which is becoming a remarkably clean story, actually. And this is exciting because really what we're seeing here is what happened 5 billion years ago when our own sun and our own solar system came into being. And so when we look at what we're going to be looking at today, it's a bit of a time machine that lets us see into our own history and some of the why behind our own existence. If we could look at the first graphic, a very important piece of this story was discovered in the 1950s by two astronomers by the name of George Herbig and Guillermo Haro. And what they found were jets of glowing gas, such as the jet here and the jet here, clumps of glowing gas rather, moving rapidly through space. What we now understand is happening is that right about where the cross is now, there's a brand new star that's forming. Material is flowing away from that star in two jets, one in this direction and one in this direction. It's called a bipolar outflow. That material is streaming away from that forming star, and then up in this area and down in this area, it's running into ambient material, the material that was around that star. This is a space telescope picture of an object called HH12, which is one of 4 different objects that we're going to see images of today. A nice thing about what we're going to see today, we're going to see images of 4 separate objects, and yet the story that's being told in those 4 separate objects is a common story. You put it all together and you start to get a clear picture that answers some fundamental questions about how it is that stars form. For example, we're going to see some data that shows us the immediate environment around a forming star, the things that might lead to solar systems and such as that. We're going to see new information that tells us about the material flowing away from those stars, and in particular tells us that that material brings with it the history of what was happening with the star itself. And finally, we're going to see a story about how that material goes out and interacts with the surroundings of the star, which might be an important piece of answering the question of what makes stars the size that they are. If I could have the next graphic. This is an object called HH34, and this is a different object from the last one that we showed you. And what you see here again is right down at about this location, right at the tip of that little arrow shape, is where the star itself is. The light that you see right around that is light that's being reflected from the cloud and the disk from which that star is forming. Coming out away from that star is an exceedingly thin jet. And one of the new results that we'll be talking about today is the fact that that jet is so very, very thin right at its tip. It tells us it's coming from the star itself almost. That material then comes streaming out through interstellar space. And if you see each of these knots along here, they sort of look like a train of motorboats, each of which has its own little bow wave. And that's a very exciting new result. When astronomers first looked at these jets, they understood that they were clumpy. But many astronomers believed that those clumps were in fact due to a smooth flow in the jet that had some sort of funny internal structure in it. For those of you who've watched a space shuttle take off, you might notice that there are little diamond-shaped features behind the shuttle main engines. We now know that's not what's going on in these jets, that in fact each one of these knots is a separate little puff of material, burst of material that came off of the forming star. And we can look at those bursts and find out not only about the jet itself, but about the source. Finally, to close up a few opening thoughts, we see jets in these forming stars, but the jets that we see in these forming stars are also very similar to the jets that astronomers see when they study quasi-stellar objects, when they study radio galaxies, when they study jets that cover millions of light years of interstellar space, and when they talk about massive black holes at the centers of galaxies. Here we're looking at the very same types of phenomena, but now close by where we can study them in more detail. Steve?
Thank you, Jeff Hester. And John Morse, what have you seen of these objects with Hubble?
Well, aside from investigating the origin of the jets, we might also ask how these jets interact with their environments and how important an impact they may have. These new Hubble Space Telescope images show us for the first time the details of the interactions between the jets and the interstellar gas. First of all, the jets travel at very high speeds, hundreds of kilometers per second, and shock waves form along the flow where it interacts with the interstellar gas, causing the jet and that interstellar gas to glow. These shock waves sweep away material from the protostar and may, in fact, restrict how much material is available to build the star. Secondly, the jets propagate for very large distances, at least several light years in some cases. They deposit considerable energy into the gas clouds, which are forming stars. And so, somewhat ironically, if you have a gas cloud which is sitting there forming stars, the actual process of star formation may wind up destroying the gas cloud. For example, let's look at the HH47 system. If we can bring up the first graphic. This is a ground-based image taken by Bo Reiperth at the European Southern Observatory. This is the outline of the cloud here, and there's a single star which is forming down in the cloud. The star is located about right here. It's invisible in the optical, but we can detect it in the infrared. This jet is driving two jets, one to the northeast, which is up here, which is slightly inclined towards us, so it comes out of the cloud and we can see it. The other jet we can faintly see right here, and it is heading off in this direction. Now let's zoom in on the details that the Hubble Space Telescope image shows us. First of all, we see that the jet has carved a hole in the gas cloud. Remember, the star's about right here, and this jet is speeding off to the northeast direction here. These white filaments are the walls of the cavity, and it's just reflecting light from the star, which is here, which is shining through the hole carved out by the jets. The real news in this story is that we can see these thin shock structures along the edges of the jet, highlighted in blue-green here. There's a series of them associated with these knots, and there's a big one up here associated with the bow wave. Now, these thin structures had never been seen before in exquisite detail that we're seeing here, and this is the first time we've been able to tell how the jet will transfer momentum to the gas cloud.
Okay, thank you, John. And Chris Burrows, you were with us last when you discovered these, or obtained a beautiful images of 3 rings around supernova in 1987A. Want to know what you have to top it today.
Well, in some ways this does top it. What we see with Hubble now is an image of a star in the closest star-forming region. So here we have a unique opportunity. This is the closest star-forming region to us, and we're looking at it with the most powerful telescope available to humans. And what we see is around the star, we see the disk of material that's falling in to form the star, and we see the jet being formed. This is the image that we've obtained, and you can see this disk here. This is the top surface of the disk, the back of the disk, and this is the front of the disk. These are both being lit up by the star that's forming in the middle here. Now we can't see the star at all because it's obscured behind the disk itself. There's a very dense band of dust between us and the star, and in fact only 1 in 100 billion photons that come from that star actually make it back out to us directly. But quite a few, as you can see, are reflected from the disk, so you can see the shape of the disk, and we're able to quantitatively model it. Then we're also able to see the jet as it comes out from the star, and as the disk collapses to form the star, it's superheated, and the jet is material that's escaping in the only free path, perpendicular to the disk. It gets jetted out in both directions, and we're able to see it as a very fine stream coming right from the star. It's unresolved even by Hubble, close into the star, which means it's got the scales of less than the size of our solar system. Our solar system itself would fit in this image at about that size there, across there. So you can see that we're seeing now on the scale of our own solar system a star in the process of forming. And indeed, when this star has formed, the material that is left behind in the disk could well eventually form planets. So, Steve.
Okay, thank you, Chris. And Bruce Margon, these are amazing pictures of jets and all. I'm sure most people haven't thought of phenomena like this very much, and when people read about how the sun might have formed or stars formed. How does this fit with how our solar system got into being?
Well, you're right, Steve, that when people think about these narrowly focused jets in astronomy, they normally think about larger scale, far more violent events in astronomy, like quasi-stellar objects that are ejecting huge amounts of material over scales of millions of light years. Here we're talking about a far more common phenomenon, indeed a phenomenon that every star has to undergo, namely collapsing from a diffuse cloud to become a star. And yet we see that these jets still occur, and they occur remarkably, even though the scale is far, far smaller, with the same very, very fine pointing and collimation. And perhaps most remarkably of all, we see these accretion disks, these flattened pancakes of gas that expel these jets. Now, the most remarkable thing that I've seen thus far is this very most recent image that Chris just shows. Maybe we could put it back up again. If I were asked to draw on a napkin for a student a disk of gas that is falling onto something and some jets that were then expelled out, this is exactly the drawing that I would make. But this is not a drawing. This is a picture. This is an image obtained by the Hubble Space Telescope of an accretion disk. Accretion is a fundamental property in astronomy. The water can't fall right down the bathtub drain. The water has to swirl around first. No matter what the environment in astronomy is, the gas can't fall right onto something. It has to swirl around first to shed its spin tendency, to shed its angular momentum. So everyone has always said these disks must form, and you draw this little cartoon. But here we actually have an image of it. This is really, in my mind, the picture that's worth 1,000 words, because this object is close enough that we can actually photograph this accretion disk.
Did we not see a year or two ago from Hubble and this very program some dark disk in the galaxy, NGC 4261, or
there have been
one object or another?
There have been previous Hubble images of active galaxies, like NGC 4261, and another one is Messier 87, where the image shows a large donut-shaped structure of gas and dust. But those are not accretion disks. Those are sort of the reservoirs of gas on a much larger spatial scale, waiting their turn to fall in. And in those external galaxies, the actual accretion disk is much, much too small to be seen, because as both Chris and Jeff have indicated, we're talking about structures about the size of our solar system. Here, this object is close enough, and Hubble's angular resolution, ability to take sharp images, is fine enough that we can actually see the pancake itself, not the reservoir.
HH30 picture is the first real picture of an accretion disk.
Certainly the first one of which I'm aware. And so, on the one hand, everyone has always predicted this, but on the other hand, to actually be able to see it and have it come out so simply and such an imitation of the cartoon that you would draw, to me, is really remarkable.
Great. Well, I think we're going to go back to Chris Burrows and find out some more. Tell us more about what goes on at the center of these stars in formation.
Well, these images actually were first captured in January of February of last year. And we were so excited to see this object that we had to come back to it with Hubble and get a second image. So one thing I'm going to show you is an image. This is actually the second image we've taken. And it's another version of the image you just saw, just displayed in a different way. And you can clearly see here these knots of material coming out from the star in the jet. And again, each pixel in this image, each little square block that you see, is about 14 astronomical units across. So that our solar system's 80 astronomical units across. So our solar system fits right in there. So we're seeing the material that might eventually form a planetary system around this star. And we're seeing the jet as it comes out from this disk directly for the first time. And it's also clear, I guess, that the jet collimation, the thing that confines the jet in this pencil beam, really doesn't have very much to do with the shape of the disk, as had been theorized. This has to be something that's happening much closer to the star than the disk itself.
Because it's much narrower than the
cavity in the disk, right.
And the little black spots along the red jet are the individual little lumps?
No, it's actually the red jet itself. Maybe we can put the image up a moment. The red spots you see are knots in the jet that are propagating away from the star, and then you can see a hint here of the jet on the other side. So these blobs we actually know are moving the other direction. Perhaps to visualize this in 3 dimensions, with John Christ at the Space Telescope Institute, Carl Stapelfelt at JPL, and Alan Watson at Lowell Observatory, I've made a simulation which I'd like to show, which illustrates perhaps in 3 dimensions, and this is a full physical model of what's going on. What you see here is the whole system rotating, so you can see it from many different angles. And we've been able to describe in 3 dimensions what the distribution of material in the disk looks like, and you can see that the model fits very nicely onto the data that we've got. So we're understanding in detail what's happening in this system. We're understanding what the density is as a function of position, and then that will help us to build models which will explain how eventually you could build planets, for example.
Okay, well, we've seen, Jeff Hester, we've seen at least 4 different Herbig-Haro objects. To the uninitiated like myself, they all look different. I suspect we'll see some more before we're done today. Is there any commonality in all of this?
Well, that's really one of the exciting things about these data. Often in astronomy, we go and look at this object and say, wow, that's wild. And then we look at this object and say, wow, that's wild. But here we're looking at a number of different objects, and we're getting the same common picture out of all of them. It tells us that we're really seeing not special circumstances, but really we're seeing a picture of how it is that stars form. As a way of seeing that, Chris was just showing you a model of what's going on in HH30 with the disk and such as that. And if we could have the next graphic here, this is exactly the same model that Chris was showing you for HH30, except this model has been turned on end a little bit. And so if you look at this model, what you see now is you see the jet coming out away from the star, very narrow at the end. You then see what appears to be kind of a conical reflection nebula here that's the top of the disk, and then you don't see the jet on the other side, because on the other side the jet is in fact hiding behind the material in the disk. When we look at HH34, which was the same object that we looked at before, we see a picture that looks very much like this model. If we could have that graphic, please. In HH34, keep the model that you just saw in mind and look at what we have here. Down at one end, the star itself is at this location, and we see kind of a conical reflection nebula, which is exactly what we saw in that model of HH30 when we turned it on end. We then see the jet coming out, again, very, very thin right down at the tip and expanding somewhat as it moves out through interstellar space. again, just as we saw in the model of HH30. And finally, we see the difference between this model and HH30 is that there's no jet here on the other side. It's actually there, it's just that we can't see it because it's hiding behind that very dense disk from which the star itself is forming. While this picture is up, the other thing that I'll talk about that's common between these observations is the picture that we're getting of these knots. Again, I mentioned in my opening comments that many astronomers thought for a long time that just a smooth flow of material was coming out from this star, and that the knots that they saw from the ground were things that were kind of happening inside that smooth flow of material. Here, though, we clearly see, for example, here a clump with its own little bow wave, or here a clump with its own little bow wave. And if you look at all of the jets that we see today, you get that same basic picture, that these are bursts that are happening, that the star does something and it spits out material. And so these bursts are not telling us something about, some esoteric piece of gas dynamics that happens as jets travel through interstellar space. Instead, it's telling us that stars, when they form, for reasons that are not entirely clear to us yet, stars, when they form from the very innermost part of that disk in the star itself, are episodic. They do something for a while and then they go burst and they send out a burst of material. And understanding the physics of why that happens is going to be something that any successful model of star formation is going to have to come to grips with.
Okay, now, thanks, Jeff. Talking about these moving knots, I think, Chris Burrows, you have a couple images that blink them for us.
Right. Well,
show us how you measured their motion.
Yeah, I actually mentioned we saw this intriguing object last February, and we were determined to come back and take a second look. So the first look that we got actually is on the screen now, and we could take a look at it. What you see here, these arrows are pointing to some knots in the jet that we saw. This was in February of '94. And then we took another image in January this year, and this is the image that we saw then. And you can see that the knots have moved. In fact, if you blink backwards and forwards between these two images, you can see the knots are moving. And because we know how long ago, how far apart in time the images were taken, and how far away this object is, we can compute how fast the jet is moving. It turns out, for example, that the top knot there, which is the one moving fastest, is moving at something like 300 miles a second, which is, if you like, 1,000th of the speed of light. So these are very energetic outflows that we're seeing, which is why they're able to propagate for hundreds of billions of miles.
So now it's not a matter of some kind of indirect esoteric guess at how quickly these blobs are coasting out. You're actually just watching the motion from month to month and month and measuring it directly. Is that right?
That's right. Although we've been able to do this on the ground, but it's always taken years and years before. You'd have to look so that you could detect this motion from the ground, and that may take 5 or 10 years. Now we're able to just measure it directly in the space of 12 months. And that means that we can follow individual blobs through the kinks in the jets and see how they behave during those changes in direction. One of the mysteries, which Jeff may come back to, is why there are these kinks in the jets, what's causing them. Now we'll be able to literally take a video of these knots as they go through the kinks and understand better whether the knots always keep going in the same direction or whether they deviate and follow along the jet as it bends through space.
And why hasn't this been done before? What would this image look like if you took it from a ground-based telescope?
Well, from the ground, you simply, the central disk that you're seeing that's yellow in the image would be unresolved. You'd see a fuzzy blob, but you wouldn't be able to tell that it wasn't just a point star. And in the knots here, remember this is the closest example, the knots here from the ground will be very difficult to resolve. They're only a few tenths of an arc-second apart.
So the whole thing would really just look like one fuzzy mushroom.
Right. You'd see that there was a jet there, but you wouldn't be able to resolve easily the individual components.
It's kind of fortunate that the nearest one has just the ideal orientation to our view, that it's in profile.
Well, there are a number of stars in this star-forming region we've looked at. This is easily the best example.
I see. Okay. I think we want to look into the physics a little and ask Jeff Hester and John Morse, what do you think makes these things come out episodically? And if you want to get into the kinks, tell us about that too.
Well, the physics is the right word. One of the very most exciting things about this is that we're finally getting a close enough look at what's going on that we can start doing some physics. For some years, people have been calculating models, using computers to do simulations of what should be happening in these jets. And they've been calculating these models, and we all go off to meetings and look at them and say, oh, that's very pretty. But then we've been turning to our data, and our data have been of such a quality that we just couldn't do a real comparison between what we were seeing in the models and between what we were seeing in the real universe.
Theory had
out
more
there.
detail than the picture.
Theory had more detail than the pictures. The exciting thing here is that we're finally actually able to see the real objects well enough to start doing that comparison. We have a simulation here, in fact. This is a simulation that was carried out by Jim Stone, who's at the University of Maryland. And what he did is calculate what happens when a jet, a pulse jet, consisting of lots of little bursts, comes flying out into the surrounding interstellar gas. And what you see here, these individual, if I could have the cursor on, please.
The little motorboats.
The little motorboats, exactly. These individual knots are the pulses that are coming out from the source. And you see that as they move along, each one has its own little bow wave, just like a motorboat has its little bow wave, which is exactly the kind of structure that we're seeing when we're looking at these jets. And so all you have to do, when we got these data, it was really exciting because we had seen these models for the past several years. And when you first looked at the Hubble Space Telescope images of these jets, it was like saying, wow, I've seen that picture before, except it wasn't a picture of something in space, really. Instead, it was a picture of somebody's calculation of what should be in space. And that's the kind of thing that when it happens for an astronomer, it's really very, very exciting because it tells you just almost instantly that there's something that now you understand that before you didn't. Another piece of that model that you just saw was the individual blobs of gas coming along and running into the bow wave at the end. So this material was coming along and one knot hit, smack, and then the next knot caught up with it and smack, over and over again. Well, when you look at another object, this is a HH1, if I could have the next graphic, please. Another very exciting thing was that we saw exactly the same phenomena there.
This is another Hubble Space Telescope.
This is another Hubble Space Telescope image. This is, in fact, a blow-up of the first Hubble Space Telescope image that I showed you. And if I could have the graphic and the cursor again, please. What you're seeing here is the jet is coming in from this direction, and it's smacking into the interstellar gas right here. And so these individual pulses are coming in over and over again. Wham, wham, wham. And what we saw here that was really fascinating is that right up here at the very front of this is the bow wave of one of those pulses, and then immediately behind it, coming right up on its wake, is the bow wave of another one of those pulses. And so not only are we getting to see the detailed physics of the jet itself and speculate about what that jet tells us about the star and the star formation, we're also getting to look at the other end of it and seeing the effects of these individual pulses coming in and one after the other running into the clouds of interstellar gas that surround this object.
Okay.
So it's really very exciting stuff.
John Morris, what causes those pulses?
Well, I wouldn't know, but there are people who might have an idea out there. Determining that, A, the jet comes from a very narrow region close to the star is a huge result in these observations. Secondly, determining that the jet is intrinsically pulsed is another huge result. It means that while matter is falling down on the star, there is some sort of episodic phenomenon occurring. Now, what that phenomenon is open to debate. There are objects such as dwarf novae, which people know are binary systems which involve accretion disks onto a white dwarf. And these objects which have accretion disks around them actually go through unstable periods, and they have outbursts. And so matter might build up, and then it would release. And then for a time, the matter would build up again and release again. So you might get episodic ejections or outbursts with a disk phenomenon. Now, the other interesting analogy with that object is that those objects don't always have the same size outbursts. Sometimes the outbursts are big, sometimes the outbursts are small, and we do see evidence for that in these stellar jets, that there are different sizes of outbursts. Perhaps we might debate that a little bit, but that's what I think are going Another phenomenon we see is that all of the jets that we've imaged, although they're straight and narrow, and how narrow they are is quite remarkable, all of the jets show signs for some sort of wiggling motion, that they don't go perfectly straight, they tend to bend around a little bit. Now, if we can bring up the HH47 HST image, we could actually see,
Hubble telescope image.
that's right, the wiggling in this particular jet is more exaggerated than the other ones we saw. To remind you again, the star is right here in the cloud, and the jet is moving off to the upper left. There's a wiggle here, another one over here. It's hard to say whether the jet actually bounces back and forth here or whether we're just seeing emission on the surface of the jet, which is actually moving along here. But there are clearly lots of wiggles and curves in here. When people look at this image, the first thing they think of is like a corkscrew. It looks like the jet may actually be spiraling, the gas are there. And we know that's definitely not what's occurring. So this jet goes fast down the middle and slow at the edges, and we have curved shock waves in the middle of the jet.
Well, John, couldn't it be what's going on is that the nozzle that's ejecting the jet is itself undergoing these gyrations?
It's possible, and immediately when you think of precession or some sort of motion of the source, you have to bring in a component.
Precession is when the axis wobbles around.
Another moving part.
You have to bring in another star into the picture. It is known that many of the sources of these jets are in fact binaries, but whether all of them are is open to question yet.
One of the exciting things is, as we've been getting ready for this presentation in the last couple of days, and we've been arguing among ourselves what it means. There are all manner of models that you can come up with.
Tell us one or two.
Okay, you look, for example, if you look at the time scales for these pulses, they range anywhere from a few years to a few tens of years. And that's the same kind of time that it takes, say, for a large planet to orbit around the star, or the kind of time that it takes for two stars to orbit around each other. But it's also the kind of time that it takes, say, for the sun's magnetic field to change directions. And we know that there's a good chance that these disks, or that these disks and jets are strongly magnetic, and that that's a major part of it. Lots of other speculation, and again, we're not giving you answers today, but instead we're saying that there's lots of neat stuff in here, and before we really say that we understand star formation, we're going to have to say that we understand all these phenomena that we're speculating about today.
I'd like to interject first that actually we do not have direct evidence that the jets are strongly magnetic. We have, in fact, no evidence that the jets are strongly magnetic. We know, I believe some work I did on my thesis